The one integral we're going to do today is to integrate 1 over x squared plus 6x plus 18. When you look at that integral, you should be saying to yourself, hey, that's a rational function. Maybe I can factor the bottom and use partial fractions. But wait a minute. You might remember from algebra that sometimes polynomials, including even quadratics, are really hard to factor, maybe even impossible using real numbers. And that actually is the case here. If you try factoring this, you will be unsuccessful. Why? Because its roots, which we can find with the quadratic formula, are not real numbers. When you simplify this, 4 times 18 is 72. 36 minus 72 is negative 36. You get the square root of negative 36, which is not a real number. Though it is an imaginary number, it's 6i. What? 6i. This all simplifies to the complex number, negative 3 plus or minus 3i. What is I? I is a number whose square is negative 1, called the imaginary unit. Wait a minute. Imaginary numbers, do they exist? Yes, we make them exist. And because we make them exist, they are just as real numbers. The first people to think of imaginary numbers, well, they had their detractors who ridiculed them. And the people who ridiculed them said, you're working with imaginary numbers. And the name stuck. But they are just as real numbers. There's no philosophical problem with their existence. The only questions are 2 questions. Well, you could say 3 questions. First of all, do they form a consistent number system that has all the algebra properties that you would want them to have, like the commutative property, for example? Yes, they do. Secondly, are they interesting? Yes, they are, in spades. Imaginary and complex numbers are some of my favorite subjects. They're amazingly interesting. Wild math in imaginary and complex numbers. Shocking, amazing math. We'll maybe even see a little bit of it later this semester when we talk about the most beautiful equation in the world. And the third question is, are they useful? That's what most people care about. Yes, they are, in spades. A little bit useful in this course, really useful in differential equations. They're useful in electronics. They're useful in quantum mechanics. They're a fundamental part of quantum mechanics. You can't really do quantum mechanics without imaginary numbers. And that's a very accurate theory that describes the world of the quantum realm of the subatomic particles. Okay? They are a fundamental part of how we describe and understand nature. Anyway, but that's just a side comment here for today and a whetting of your appetite for the future. At the moment, it means we can't factor this. So we need some other technique to do this integral. How? We can't factor it. What can we do? Well, maybe we can try to rewrite the bottom of this fraction in a new way, like maybe vertex form. Would that be helpful? It's something worth trying. How do you write it in vertex form? You complete the square. Focus on the first 2 terms. Ignore the plus 18 for the moment. For that part, it's not a perfect square, but you might remember completing the square is to make it as something squared. How? If the coefficient of x squared is 1, the simplest case, which it is, yay. Then you take the coefficient of x, 6, and it's a 2-step process. Divide it by 2 to get 3. Square that number to get 9. And then, oh, this is so fun. Just stick that 9 in there. Like that, and now it's a perfect square. But wait a minute. How can you do that? How is that allowed? What about the plus 18? These are not equal. Well, you just compensate. We've added 9, so subtract it. Right? Tricky math. By doing this, we have written what's in parentheses as a perfect square, x plus 3, quantity squared. 18 minus 9 is plus 9. All we've done is rewrite the function. These are the exact same function. They just look different. But because of this, it's starting to look like it might be related to the integral of 1 over 1 plus x squared. Maybe the answer involves inverse tangent. Yeah, it does. Oh, but what about the plus 9? And what about the fact that it's an x plus 3 instead of an x? We can deal with those things. A little bit more tricky math. We can factor out the 9. And maybe I'll feel like putting the 1 in front to make it more similar to the way we usually write it. It would be x plus 3 squared over 9, which is the same as x plus 3 over 3 quantity squared. This is just a weird, fancy way of rewriting the original function in a way that's going to be easier to integrate, even though it might not seem that way. I'll factor out the 9 in the bottom there as a 1/9 in front of the integral. Okay, now we want to use a substitution. You know, if that were just a plain old x squared, this would be easy. Or if it were a plain old w squared, it'd be easy. How about we let w be x plus 3 over 3? 1/3 x plus 1. Then dw would be 1/3 dx. So dx would be 3 dw. I think I can do that integral now. 1/9 times the integral of 1 over 1 plus w squared times 3 dw. 1/9 times 3 is 1/3. Integral of 1 over 1 plus w squared is going to be inverse tangent of w plus c. Final step, replace w with x plus 3 over 3. Okay, as always, let's check that we're right. Try it a couple ways. Let's see what the integral symbol button does to the original function. 1 over x squared plus 6x plus 18. Looks good. You can also do the capital D for differentiation if you wanted to. Arctangent's the same as inverse tangent. Okay? So it is doable. There are techniques that are, you know, they were probably just originally discovered by somebody just experimenting, problem solving, and eventually they happened upon the technique that worked. Now we're getting you there faster by saying, hey, here it is. Here's how you do it.